video course on tribology. Today's topic or today's lecture's topic is selection of rolling element bearings. We have discussed in previous lecture about rolling element bearing. Some description was given about rolling element bearings, but selection is important. We need to select proper bearing for proper application or for our application. So we are going to discuss that selection criteria in present lecture. Few points which we have already discussed will be repeated for proper guidance. We started one example in previous lecture, and I'm just repeating the same slide over here. We say that assume there is some radial load and axial load on a bearing. Bearing load is coming perpendicular to the axis as well as along the axis. The magnitude of that load is also defined. Say 7.5 kilonewton is along the radial direction or perpendicular axis, and 4.5 kilonewton is along the axis. Shaft diameter is given, and you are saying the shaft is rotating. That means inner ring is going to rotate. What we need to do, select a suitable single row deep groove ball bearing. Now in this case, we are not going to select the bearing among the gummits of the bearing, only from deep groove ball bearing. One category of bearing, that's a deep groove ball bearing. More like we are going to choose different dimension, or we are going to select from the different dimensions what will be the proper bearing for our application. So in this case, the shaft diameter is given, the bearing bore diameter is defined in this case, and based on the bearing bore diameter, if we select the bearing, that is a 1/4 series, because we know to find out the bore diameter we need to multiply last two digits with a 5 number or number 5. So 14 into 5 is a 70. Similarly, 1/4 into 5 70, 1/4 into 5 70. All the bearings have a bore diameter of 70 mm. We are going to choose a bearing among these bearings. Now, in this question particularly, we don't have any shielding requirement or sealing requirement. That's why we have removed the option 2RS1, 2RSZ, 2RS1, 2RSZ. All these options were removed. Remaining options are 61814, 61914, 16014. It was described previously. These are the special type of the bearings, generally manufactured for one particular company, and then if it is already mass produced, technique has been developed or manufacturing process have been developed, then we particular company will open it to the open market to other people also. Similarly, bearings are also there, the 6014, 6314, and we need to select one of this bearing. To select bearing, we require rating, particularly based on axial load to the static load carrying capacity. That's FA is axial load, C0 is the static load carrying capacity, and static load carrying capacity is defined over here. So 13.2, 25, 31, same thing in this case, 45, 45, 68. And as the inner ring is rotating, it says the shaft is rotating, that means inner ring is going to rotate. Inner ring is rotating, that rotation factor will be equal to 1. Coming to the single row side, we have, as a question says, we need to select a single row deep groove ball bearing. So we need to find out what is this ratio FA by FR. In our case, this ratio FA is a 4.5 divided by 7.5, and we need to compare with this parameter. This E parameter is generally defined on the geometry of the bearing. If this ratio FA by FR is greater than E, then we will choose X parameter and Y parameter and try to find out equivalent load. In previous lecture, we did that similar thing. We said the FA by FR is a 0.6. In most of the cases is more than what is given as a FE parameter. That means we have to select a parameter X and Y from this. Then we require FA by C0. as individual bearing have particular or typical value of C0. Naturally, if I am choosing, suppose I want to find out bearing from this category, I'll just pick up the two examples, 6014, 6314. Now we need to choose a bearing, and we need to find out which bearing is going to perform better, even though we have other options also. Just for example, we picked up only two bearing for time being, the 6014, 6314, and C0 is defined. First case it is a 31 kilonewton, and the second case is 68 kilonewton. That's why it is given over here, the 4.5 kilonewton divided by 31 kilonewton, 4.5 kilonewton divided by 68 kilonewton. And when we find this ratio is not coming, it's not exactly matching any of this value. So we need to do some interpolation. This is what in the first case, this value is turning out to be 0.145, which is not equal to 0.11, it's not equal to 0.17. That's why we required some sort of interpolation between these two to find out exact value of this. Based on that interpolation, we can also compare with the E value, find the correct E value from the interpolation, and based on that we can compare, and we can say what will be the parameter x and what will be y. We know x is not changing at all, so interpolation doesn't mean much to this. X will be exactly 0.56, while y will be different. It will be somewhere value between 1.45 to 1.31. In correct manner, we say that value will range or will be greater than 1.31 but lesser than 1.45. And what we find from our catalog, this value is a y value is a 1.37. Similarly, we can find out this ratio FA by C0, that is a 4.5 divided by 68, that is coming out to be 0.0662. Again, we are not able to get exact value, this exact value over here. We have value the 0.056 and 0.084. We need to do interpolation to get this value, and with that interpolation we will be able to find out the correct value of y, which will be ranging between or will be greater than 1.55 but lesser than 1.71. And what we get after interpolation, that is a y is equal to 1.65. Now using this parameter 0.56 and 1.37, I can find out equivalent load. How to find out equivalent load? This x need to be multiplied with the radial load, that means 7.5 kilonewton into 0.56 plus 4.5 kilonewton as axial load into y, that is a 1.37. This summation will be equivalent load, which is turning out to be 10365. Same thing for second bearing, which is a 6314. We have x is equal to 0.56, same multiply with the 7500 newton. Second will be as 1.65 into 4500 newton. So it will be summation the 0.56 into 7500 plus 1.65 into 4500 newton. A summation turn out to be 11,625. And previously, so as I mentioned, if I want to select based on the applied load bearing, the first bearing will be a proper choice, because in this case equivalent load is lesser than second bearing. First case is a 10365, which is a lesser than 11625. But this is not all. We need to find out how to choose a proper bearing based on other criteria also. In this case, it is only the load, or we say equivalent load. And equivalent load states that this is a better bearing because equivalent load is a lesser, and we know very well that lesser load will be preferable for the bearing life. So the question comes, how to estimate the bearing life, or if the life is given or estimated life is comes in the question, then how to proceed further. For that purpose, this is the next slide. It says that consider the shaft rotational speed. Generally, bearing life is given in rotations. It's a dynamic load, it's a fatigue load. So how many rotation that bearing can survive? Naturally, we require rotation per minute reading, as well as how much life is expected. In this case, this question has been added with 1000 RPM, as a rotating speed of the shaft, and expected bearing life is a 3000 hours. We require bearing to survive without any pit on the surface for 3000 hours or minimum of 3000 hours with a 90% reliability. Of course, if the reliability increases, naturally we know that we have to count a parameter A1, which was discussed in previous lecture, that need to be accounted. So when we add these parameters, we need to consider the life equation, which was derived in previous lectures, and that is equivalent to this equation. We say that this C is a dynamic load carrying capacity. That means bearing can survive for 10⁶ cycles for this kind of a load. And A is decided based on whether the geometry is a ball geometry or the roller geometry. For ball bearing, A is equal to 3, while for roller bearing, A is equal to 10/3, that means 3.33. That's a slightly more than ball bearing, because we know roller bearing can sustain slightly more load compared to the ball bearing. Same relation for the other loads. We know the V1 is a lesser than C L1 will be greater than 10⁶. Similarly, for other cases P2, L2, P3, L3, we can utilize this relation. Now, using the previous slides, we can find out what is equivalent P. We can substitute the value of P, and L1 is already given to us, what is expected life if we convert in a rotation. To convert in a rotation, we are using this relation. What is that? It says that we are counting the speed. We know this is a 1000 rotation per minute. If I multiply with a 60, then in that case it will be 60,000 rotation per hour, and we require bearing life in hours. That's why this equation has come. Bearing life in hours, because we require 3000 hours, can be rearranged such a way, C by P power A. That means here we are more important about the ratio of the C by P. It is not only the value of P, but what is the value of that bearing, or what is the value of C for that bearing is important. This ratio is important for us. For both the bearing, the speed will remain same, because same we have to mount on the same shaft. The shaft speed is given, that's defined for us. So we need to select a bearing based on C by P ratio in this case. Of course, other cases also will come when we consider the friction, or we say that we require low friction but high load carrying capacity. Naturally, bearing choice will be different than what we are doing it. Just now we are concentrating on the load, and we are concentrating on the bearing life. If bearing life is 3000 hours expected, naturally C by P is going to be a dominating parameter in this case. So for two bearings, what we given in we picked up in the previous slide, that is 6014 and 6314. We know very well 63 is a high bearing load carrying capacity series. It will be dimension will be more than 6014. Actually, if there is a space say the consideration comes, or there is a restriction or constraint on the space, then we had to also choose accordingly. They say that we don't have a more space available, diametral space, we had to keep in within this envelope dimensions. Naturally, we had to choose that bearing, from that angle that bearing. However, in this question nothing has been defined. We are free to choose bearing. There is no restriction on the dimensions. Now for 6014, the equivalent radial load turned out to be 10365. However, for a 6314 bearing, it was a 11625, and based on this criteria, equivalent criteria, we say that this bearing is a better option compared to this bearing. Now, we are counting C because we are interested in ratio of C by P. C for 6014 is a 39,700 Newton. It's more like 3 times, or maybe 3.8 times of this. Well, coming to this side, dynamic load carrying capacity, that is C, is equal to 111,000, or say 111 kilonewton, which is almost 3 times of this. So here slight increase in the P, but here the major increase, a more increase in the C. That means we are going to get a better value of C by P for this kind of bearing. Naturally, this bearing is going to survive for much longer time compared to this bearing, because if this ratio is a higher, then there is a power series also, is a cubic series. Naturally, if this ratio is more than 1, A will always be in a favorable situation for us. So if I substitute all this value, if I substitute C over here, P over here, the speed is already defined as a 1000 RPM, we'll be able to find out the relation, or we'll be able to find out whether this bearing can survive for 3000 hours or not, or this bearing can survive for 3000 hours or not. If we do that, what we are going to get 937 hours for the first kind of bearing, that is a 6014 bearing. 937 hours, which is lesser than 3000 hours. That means this bearing cannot be selected for our application. We are defining is for the 3000 hours. However, if the bearing life, estimated bearing life was 6 hours, 600 hours, 700 hours, 800 hours, 900 hours, okay, this bearing is a better option because it has a lesser envelope dimensions, and naturally it will be lesser costlier compared to this. Then coming to this bearing, we have a much longer life as a 14509 bearing. Actually, this is a much long, we say the high speed coming over here with operating hours almost 5 times compared to what we require. We can go ahead with some other bearing like a 6214 bearing, which will show lesser dimension as well as have a lesser life, which will be more than 3000 hours. So based on this example, we can say that equivalent load as well as the operating hours should be considered when we go for the bearing selection. That is important for us to choose a proper bearing. In this case, what we have picked up the 2 bearing, one is not able to sustain or survive for the life which we require. Other bearing is showing much longer life compared to what we require. Naturally, an intermediate bearing or in between bearing which will be coming in the catalog should be selected or should be checked first and then selected based on that. So that is giving some idea how to choose a proper bearing for our application. In addition, there are some statements which generally we could or which we specify, or some notes generally we specify. The thumb rule: applied load equivalent radial load should be lesser than 10% of C. That's a recommendation. It should be lesser than 0.1 times C. If the load is more than that, bearing life will not be much. So the thumb rule says P need to be lesser than 10% of C. And here if you can see, this is a 39,700 and this is a 10,365. The ratio will be coming 3.5, 36.8, something like that, which is much larger than what we require. In this case, applied load is very high. From that point of view, this bearing is not selected or cannot be selected. So there is another way. If we know what is a P and what is a C, directly based on that ratio we can say, oh, this bearing will not give a good life, so we should not select it, we should not move to towards that direction, we should reject this bearing at the first instant. We don't have to do this kind of calculation. So coming to other side, we say the bearing need to sustain some load. However, there will be some sort of a vibration because we know the rolling elements will be having some separation from inner ring and outer ring. There will be some clearance. If there is no load, there will be a lot of vibration, a lot of noise. That's why there is a need of some load on that. And of course, there is no firm rule that P need to be exactly like this, because we have seen a number of books and we find that everywhere this value is different. Thumb rule says that it should be greater than 3% of C. It should not happen that you are applying very low load on a bearing and bearing is making a lot of noise. In that, because of noise and the noise as well as the vibration, there is a possibility of early failure of the bearing. So it should be avoided. However, as I mentioned, this is not a firm rule, 0.03, because we have seen the SKF catalog. They recommend 0.02 C to be imposed for the roller bearing. The roller bearing minimum load need to be 2% of C. However, slightly lesser is being applied for the ball bearing. Here the ball bearing they recommend 1% of the C. The load need to be more than 1% of C, and for roller bearing it need to be more than 2% of the C. Of course, there are too many parameters involved, too much geometry involved in that. Doing a detailed analysis will give the right value, but as a thumb rule or the starting purpose, we can say, okay, P as far as possible from economic point of view need to be more than 3% of the C. We can stick to that rule. There is another consideration, or you say that this bearing life have been estimated without correction factors. What we say, the life adjusting factors. We assume here bearing life for the 90% reliability. If we require other than 90% reliability, that factor should come over here. Similarly, we are assuming there is an ideal lubrication. Whatever the lubrication, wherever the lubrication is required, that is getting supplied or that is being fulfilled completely. But there is a possibility of a starvation, there is a possibility of excess of lubrication that has not been counted over here. So, there will be some factor counted over here. Another thing is that we are assuming the bearing material is perfect. There is no crack formation, there is no manufacturing related problems, and then the kind of the material which we are using is perfect. If material is not perfect, then that factor also should be accounted. However, most of the industries, they go ahead with the better material, and the material parameter or material factor is generally equal to 1. We need to adjust this bearing life for the reliability as well as for lubrication parameter. For lubrication related aspect or lubrication parameter, we will be discussing when we will start a lecture on the lubrication of rolling element bearing. For time being, we are assuming this relation, we will be carrying this relation for the next calculations also. We discussed something about the deep groove ball bearing, and that is it gives a good positional accuracy and is a cheap one. It is more like low cost factor, readily available in the market. However, there are some other bearings also with having some more contact angle, and we are trying to show how other bearings are better than deep groove ball bearing when there is an axial load. These deep groove ball, this kind of the bearing which can sustain some axial load, having some contact angle. Contact angle can be 20 degree, 30 degree, 40 degree, 50 degree, depends on the which bearing we are going to select. That's why this bearing are known as angular contact ball bearing. This is the first picture shows this is angular contact, and if I draw a line perpendicular to the axis of this ring, we find that this is not merging with a load axis or with a contact axis. There will be some angle between this. This is a single row. Similarly, we have a double row also. Two row bearings, which naturally we know very well load carrying capacity of the two rows will be higher than the single row because they have a higher number of rolling elements, and moreover load will be shared. Naturally, load carrying capacity of this bearing will be higher or on higher side compared to this bearing. There is another option available. We say that instead of going for this kind of bearing, we want what we want. We want more contact, particularly in for axial direction. Why not we go ahead with the 4-point contact bearings, which can sustain some axial force as well as a radial force, and also it is advisable from a size point of view. They don't have as high size as these kind of bearings. So we can think about the 4-contact ball bearings or 4-point contact ball bearing, double row angular contact bearing, single row contact bearing. Depends what is a requirement. If the load requirement says that we don't have an axial force, naturally we will not choose any of this bearing because they are going to show a higher coefficient of friction. From friction point of view, these bearings are less advisable or lesser advisable compared to deep groove ball bearing compared to roller bearings. Now, there is some sort of a specification. If we see some catalog, and in this case we are referring a SCAF catalog, that for contact angle, they don't write the contact angle at 40 degree, don't write the 25 degree, don't write the 30 degree. What they give some sort of suffix at the end of the bearing series, and then for 40 degree they give suffix equal to B. Also the B, if you find any time bearing with a B specification in a suffix, we say, oh, contact angle is a 40 degree. Similarly, if the contact angle is a lesser, that's a 25 degree, then it will be known as a AC series, or the suffix will be with the AC. And if the contact angle is 30, then the suffix will be A. So if we are just scanning through the catalogs, we can say, okay, what will be the contact angle, because for our calculation purpose we require a contact angle, so that we can figure out whether what will be the contact life of the bearing. Just now I discussed in a previous slide about double row contact bearing, or is it the angular contact bearing, and double row contact bearing. That is these are three arrangement have been shown here. This is a tandem, which is that bearing is supporting or is enhancing the load carrying capacity in one direction in this case. Now they are in the same arrangement. There is other possibility of back-to-back arrangement or face-to-face arrangement, or sometimes it's known as a O bearing and this is known as a X bearing. And if you see the previous slide, this is what we are saying, that double row, O bearing, X bearing, tandem bearing, and these all three bearing are shown in this slide. Say there is a tandem arrangement, there is a back-to-back arrangement, there is a face-to-face arrangement. Every configuration has its own advantages. What we say that back-to-back bearing is going to provide, back-to-back bearing is going to provide more and more rigidity, more and more attachment or fixation of that bearing, right? And that's why the primary factor is that we require rigid mounting. We don't want the shaft kit is deflected or displaced anyway, then we should go ahead with the back-to-back bearing. Well, in this situation, particularly inner ring need to be claimed. The outer ring is rotating naturally. From a load point of view, this is not very highly recommended. From positional point of view, this can be recommended. Coming to the face-to-face bearing, in this case, what we are going to get is some sort of flexibility in outer ring. That means we can allow some sort of misalignment in this kind of bearing. There is a possibility of slight misalignment. What will happen in this case? The roller or this ball will get shifted to one side. It will be losing a load carrying capacity for that, but it can sustain some misalignment because of this kind of the groove. And in this case, outer ring will be clamped, so that this will be preferable choice for general purposes. And if we require especially positional accuracy, then we can go ahead with this kind of bearing arrangement. This is giving an introduction of some sort of description about when the two bearings are arranged, either in tandem arrangement, that means they are supporting the load in one direction, or in the back-to-back arrangement, or the face-to-face arrangement. If I compare all this bearing, what we say the 4-point contact ball bearing, double row angular contact bearing, single row angular contact bearing, and single row angular contact bearing for the pair mounting, for the tandem mounting. Whatever we showed in previous slide, the pair mounting or tandem mounting. And for the same diameter, of the shaft, which is assuming that this bearing is going to get mounted on 25 mm diameter, all the bearings are 05 series. That's why it's shown here D 25, 25, 25, 25. Now, outer dimension, that's enveloped outer dimension of say the final dimension of outer ring is also same, the 52, 52, 52 mm. Coming to the length side, so 4-point contact bearing is a 15 mm. Coming to the double row, it is 20.6 mm. Single row angular contact bearing, which will be naturally lesser than this dimension, that is a 15 mm. Coming to the pair one, tandem bearing arrangement, that has a 30 mm. So that means from dimension point of view, from axial length point of view, naturally this bearing should be recommended and this bearing should be recommended, but not this bearing, not this bearing. But this is only the space consideration. We are concentrating on the space. Coming to the dynamic load capacity, or C. In this case, particularly the dynamic load is capacity is 25 kilonewton. Well, here it is just 21 kilonewton. Coming to this side, it is a 15.6 kilonewton. We say lesser than 16 kilonewton, which is least in this bearing configuration. And a single row angular contact bearing occupy the same space as a 4-point contact ball bearing, same outer dimension, same bore dimension, but load carrying capacity is inferior compared to this. The 25.1 kilonewton, here the 15.6 kilonewton. Naturally, this bearing cannot be recommended in compared to the 4-point contact bearing if we are not considering the friction losses. Naturally, if we consider friction is also having highest importance, then in this situation this bearing cannot be recommended. This bearing can be recommended based on the load. This bearing can be recommended based on the life estimation. The life will be higher in this case. Coming to the static load capacity is also almost 2 times compared to this. That means there will not be much plastic deformation compared to this, or we say that plastic deformation in this case will be lesser than this case. However, coming to the 430 with the fatigue load limit, let's choose also the fatigue load limit for the 4-point contact bearing is higher compared to this. Only the problem is running speed. There was a 9500 running speed for the 4-contact ball bearing. Reason being it has a higher friction and will generate a high heat if you try to rotate on a higher speed. But in this case, it's 10,000. In case of the in presence of oil, is a 14,000. In presence of oil, single row angular contact bearing is showing 15,000. So if I compare 4-point contact ball bearing with a single row angular contact bearing, other than friction, this bearing of 4-point contact bearing is showing a better performance. So we should select this kind of bearing. However, the other parameters, so the cost, other parameters also like availability in a market. If a bearing is not available in a market or very costly, and we don't want to invest that much money, then we need to think about a different way. But from load point of view, from my estimation point of view, 4-point contact ball bearing is preferable compared to single row. Coming to the double row, we are able to see in this case the length is increasing by roughly 25% to 30%. In this case, the same thing is happening in the load carrying capacity. That means we are not going to gain much advantage from the double row angular contact bearing. Slight increase or some increment in load carrying capacity. Similar increment is happening in the length side. So this is double row angular contact bearing is not giving that much profit as what is expected. Coming to the paired bearing. Paired bearing, we say that we are giving too much length. The two bearing have been combined together. Head or for pairing cases, there is some decrement in the load carrying capacity. Instead of 15,600, now it's not 2 times in 2 into 15,600. Slightly lesser than that, 25.1 kilonewton, which is lesser and which is almost same as what we are getting in a 4-point ball bearing. Now, if I compare 4-point contact ball bearing with a single row angular contact bearing for the paired arrangement or the tandem arrangement, what we are going to lose? Length is almost half. Load carrying capacity is almost same. Either dynamic load carrying capacity or static load carrying capacity. Fatigue load is almost also same. So we are not gaining much if we are choosing the paired bearings. Here, this bearing will be better option compared to this bearing. So what I am trying to conclude from this slide is that we need to see all kind of the bearings. We need to find out what is the exact requirement for us, and it's sure for our requirement we will be finding a number of bearing, and later we want to add the friction aspect, we want to add the cost aspect, we want to add availability aspects. Based on that we can make a final selection. But if those selections or those criteria are not dominating criteria, or cost is not a major factor, then we can choose the best bearing based on the load and based on the life estimation. Now, this slide shows how to choose an angular contact ball bearing. These are just a repetition of previous one lecture slide. So that for different contact angles, x and y factor will be different for single row as well as for double row. When we are talking about the double row, both the factors are accounted. Whether this ratio is greater than E or lesser equal to E. That means for the cases we need to consider xy factor. However, when it is lesser than E, x is equal to 1, that we need not to be considered. We can say directly Fr plus y into Fa. That can be used whenever there is this ratio is lesser than E or equivalent to E. So based on that we can find out the equivalent load, we can choose a proper bearing, and I am going to show the deep groove ball bearing and angular contact ball bearing comparison. You can show the deep groove ball bearing, which is generally a typical choice of designers, may not be a good choice when we think about science, when we think about proper tribological knowledge. For that purpose, I am considering this example. What is this example? Is that let's consider a bearing is subjected to 3000 Newton radial load with thrust load equal to 2500 Newton. You can see the ratio 2.5 divided by 3. That's a very high ratio, more than 0.8. Is to be carried by the one deep groove ball bearing a 6214 series bearing. For as already mentioned, shown over here, is the last two digit is a 1414. If you multiply with the 5, naturally we are going to get a 70 mm. It is for 70 mm shaft rotating, which is rotating at 1000 rpm. So in this case particularly, the inner is rotating. Naturally V will be equal to what? Determine equivalent radial load to be used for the calculating fatigue life, or for estimating fatigue life. We can find out, first we need to find out equivalent radial load, that's equal to P. Compare life of this 6214 bearing with that of 7214 bearing, that is the angular contact bearing, and here the contact angle is a 30 degree. That means whatever we choose from catalog, we need to choose for the 30 degree contact angle. If we scan through the catalog, what we find, C0 static load carrying capacity for 6214, that is the bearing which we have been defining over here, is 45 kilonewton, and for the 7214, this bear static capacity is slightly on higher side, that's 60 kilonewton. Now we say that is almost 25% plus or more than 25% higher side compared to the C0 for the 6214 bearing. Coming to dynamic capacity, that's the value of CC for the 6214 is 63.7 kilonewton, and for the 7214, this bearing load carrying capacity is 71.5 kilonewton. So from this load comparison clearly indicates that actually 7214 bearing is going to be a better bearing compared to this bearing. Just by scanning catalog, we can find that 7214 bearing is going to show better performance compared to 6214 bearing. Now we need to find out what are additional advantages. This conclusion is based on the C value. 7214 bearing C is 71.5 kilonewton, which is greater than 63.7 kilonewton. As a load carrying capacity or dynamic load carrying capacity of this bearing is higher, naturally 7214 bearing should perform better. Now we need to find our second option, that's we say what will be the equivalent load, because as we earlier mentioned, bearing life will always be depending on the C by P ratio. We are showing here C is higher side, but what is the value of P? We need to find out that. And to find out that equivalent load, we require X parameter and we require Y parameter. To find out X parameter and Y parameter, we need to find out what is F by R. F by R in this case is 2.5 divided by 3, which is need to be greater than E. If it is lesser than E, then we need not consider equivalent load, or we say that FR will be equivalent load. Now we have considered two bearings, the deep groove ball bearing and angular contact bearing, and static capacity as well as axial load has been defined, so we can find out this ratio. In this case, our F by C0 is a 0.056. For angular contact, is a 30 degree angle we know, and based on that we can find out this parameter X and Y. So for X parameter for deep groove ball bearing is a 0.56. That means we have to consider 56% of radial load FR, while Y parameter is a penalty. Penalty is coming at 71%. If we are not just adding the FA, we are penalizing the FA with a 1.71. That means enhancing FA and then adding to the radial load. We are not doing a simple combination, and in this case this E is equal to 0.26. Naturally FA by FR is greater than this, that we have to choose X and Y parameter to find out what is the equivalent load for 6214 bearing. Coming to the angular contact ball bearing, a 7214 bearing, we need to choose 0.39 into FR plus 0.76 into FA. Now when I do this kind of study, it's clear, oh, this parameter is a lesser here. We know FR is same for the both the bearing. Applied load remains same for the both the bearing, but X parameter in this case is the lesser. Naturally, we are going to get a first component of equivalent load lesser for this bearing. Coming to the second component is the 0.76, which is again lesser than 50% of this. Naturally, equivalent load which is required for us is will be lesser for the angular contact bearing. So, in that case, we are getting a win-win situation. First thing is the C is on higher side and P is on lower side. Naturally, C by P ratio will be much larger for angular contact bearing for 7214 bearing. Naturally, life estimated or estimated life for the bearing for angular contact bearing will be much larger compared to deep groove ball bearing. So, this analysis also indicates we are going to the right direction. If we replace 6214 or so the 7214 with 6214, or we replace deep groove ball bearing with angular contact bearing, which will be better option for us. So, whatever I mentioned in previous slide is same thing over here. FR is a 3000 for the both the bearings. X is a 0.56 for the deep groove ball bearing. For angular contact bearing is 0.39. So, we can multiply 3000 into 0.39. Actually, this multiplication will be lesser than multiply 0.56 into 3000, because of this parameter is lesser than this. When we add, we had to multiply and then add with this is a 1.71 into 2500, while in the second case it will be 0.76 into 2500. Again, this product is a lesser, this product is lesser, naturally summation will be lesser. And when we find that is for radial load or equivalent radial load for 6214 bearing is a 5955 Newton, while for 7214 bearing this load is a 3070. It's almost half of this bearing. Actually, we are going to see, or we are going to estimate the bearing life much higher, longer, or much higher compared to 6214 bearing. We do that kind of calculation. We know what is the speed of operation. That's a 1000 RPM. We already calculated C, or we figure out the C from the catalog. P has been estimated or calculated. We can find our bearing life in hours, and that is for the deep groove ball bearing is a 7192 hours. Not very low life, but not as high as a second bearing. That shows 124,420 hours. So, we can compare 7 versus 124. Cost will not be that much higher. Availability will not be that much problematic. If we, for this kind of load carrying capacity, or for the whether axial load is on the higher side, is a ratio FA by FR is almost a 0.8 or plus, then we should choose angular contact bearing compared to deep groove ball bearing. As I mentioned earlier, deep groove ball bearing is easily available, and often designers choose a deep groove ball bearing, but slight more consideration, slight calculation indicates that is not right choice. Right choice will be angular contact ball bearings, which is a better option, or the much better option compared to the deep groove ball bearing. Right? Of course, this is just a simple thing that if we want a life in number of hours, we need to find number of days. We need to find out how many operating hours in a day, is of 8 hours, 10 hours, 12 hours, 16 hours. Based on that, we can find out how many how many days this kind of bearing is going to survive. And generally, for the machines, we calculate the bearing life in number of days, not number of hours. Now, there is another, we have calculated equivalent load, equivalent radial load for static load carrying capacity. We say that when the applied load is static, it is not going to fluctuate in magnitude as well as in direction. Applied load is always on pointing with one direction and having constant magnitude, either radial load or axial load. Whatever we have considered a combination, and based on that combination, obviously using those parameters and XY parameter from catalog, we calculated what will be the equivalent load carrying capacity. There is a possibility load magnitude changes. We say that bearing may be operating at the load P1, P2, P3, P4 for different hours. That is why it is given here. Bearing operates at a 1000 RPM for applied load equal to 500 Newton. This 500 Newton has been applied for 100 hours. That means for 100 hours, applied load was 500 Newton and operating speed was a 1000 rotation. Then some change in the system, some different operational requirement. See that in that case, bearing operates at 1200 rpm, slightly higher rpm compared to this, but lesser load 215 Newton, and operating hours are more. Instead of 100 hours, now the operating hours are 250 hours. In this situation, how to estimate bearing life? That is a big question. Here we don't know what will be the equivalent load. To find out the equivalent load, we use this equation. You see, we know what should be the final life of your 10⁶ cycle or operating hours based on whatever we require. Maybe we say that for L1 number of rotation, bearing is subjected to P1 load. For L2 number of rotation, bearing is subjected to the load P2. For L3 number of rotation, bearing is subjected to load P3 and so on. So, what will be the bearing life? Estimated bearing life will be required L1 plus L2 plus L3 plus L4, L5, whatever number or final number comes, or maybe a repetition of that also. So, based on that, we can find out what will be the equivalent load, and this has been derived the same pumpkin equation. We are able to estimate equivalent load based on this relation. This is what we to simplify this relation, what we can do, we can say, okay, let's assume L is expected life. If L is expected life, we can divide numerator as well as denominator with L. That means here the summation will be L1 plus L2 plus L3 plus L4, L5 and all, and this is overall life. So, this ratio will turn out to be 1, because all the summation of L or else will be equal to L, and that L divided by L will turn out to be 1. While here what we are going to gain, L1 divided by L, that means we are seeing the fraction of the life. 10% of the life will subjected to load P1, 20% life is subjected to load P2. So, that fraction is important for us. So, that is why I say L1 divided by L is F1, L2 divided by L is F2, L3 divided by L is F3. And now, if we know F1, if we know F2, if I know F3 and the loads, corresponding load on for those many number of rotations, we can find out what will be the equivalent load. Once I know the equivalent load, we can find out the operating life. Here is the total number of cycles, and then we can find out the bearing life in number of hours, number of days, number of rotation, whichever is requirement. But here again we are assuming the life bearing is subjected to load for the some time. It is not a repeating, it is not continuously changing. For L1 rotation, the bearing is subjected to load P1, more like a static load, but magnitude is changing after certain rotations. There is other possibility. Load is changing magnitude from P max to P minimum in the average rotation, say maximum load and minimum load. In that case, we do not use a summation of P min plus P max divided by 2, because we know higher load is much more harmful compared to lower load. That is why we go ahead with this kind of ratio, say 33% of the P min and 66.6% of the P max. Again, we are not directly going for all complete maximum load. We know the bearing is a fatigue, is subjected to fatigue. A lower load will always be helpful. So, we want to count that, and that is why we say the equivalent load for dynamic cases. Dynamic case in the sense the load is continuously changing, is changing between the P max and P min in one rotation, then we should count equivalent load based on this relation. However, there is another possibility, a combination. You say P1 is a constant load the way we have considered in the previous lines, but P2 is a rotational load, and every degree this load is changing its direction. So, this is not magnitude is changing, but the direction is changing. That is why we have divided P1 constant load always directed to one direction, while P2 is continuously changing. So, in that situation we use this relation. This relation shows here the P2 1 plus 0.5 in bracket P1 by P2 is square of that. Similarly, in the second, the P is equal to P1 1 plus 0.5 P2 by P1 square of that. Question comes, when should I use this relation, when should I use this relation? This is for the only this situation, and P is a constant load, P2 is a rotational load. Again, these are the curve fit equation. There's no complete science behind that. It has been based on experience. Now, wherever the dominating factor comes, if the P2, if the P2 is much larger than P1, then we should use this relation. If P1 is much larger than P2, then we should choose this relation. What is the overall thing? Or sometimes people can think, oh, what will happen if P1 is equal to P2? If P1 is equal to P2, we can choose any of this relation, because both the relations are going to converge to the same solution, same results. You can see P1 is P2, this will be 1 plus 0.5. Now here the P1 and P2, the same relation. So whenever P1 and P2, I can choose any of this relation. When the P2 is greater than P1, I will choose this relation. When P1 is greater than P2, I will choose this relation. So depends on what is the magnitude of P1 and P2 and compare it, and based on that we can find out what will be the equivalent radial load carrying capacity or equivalent load capacity required from a system. Now once we know P, we can estimate the bearing life. Let's have an example. So in this case, we are saying the one ball bearing is running at a 4 piecewise loads. What's the piecewise load? We say that in first case it is subjected to load of the 4 kilonewton for certain rotation, maybe say when it is operating at the 1000 rpm, and for the overall time is for 10% of the total time is running at the 4 kilonewton. For the 20% of total time, it is running at 2000 rpm, but lesser load, that's a 3 kilonewton. For 30% of the total time, this bearing is running at 3000 rpm, when applied load is a 2 kilonewton. For 40% of total fraction of time or total time, it is running at the 4000 rpm and applied load is a 1 kilonewton. Here we require F1, F2, F3, F4, nothing has been given. So what we need to do? We need to find out first rotation. How many rotation at this load? Naturally, 0.1 time into 1000, we are calculating. Based on that, we find that this product is giving 100. Here again the 0.2 into this rotation or this RPM is in the 400. But we are saying that the number of rotations are increasing. Now we don't need final number of rotation for time being when we are trying to find out equivalent load. Final number of rotation we require when we trying to find out overall life. In this case, we are just calculating a fraction, or we say that a ratio. Here the 1 into 2 is the time, if I am assuming the minutes, or maybe this is a dimensionless as such, but if I assume from that point of view, this is the 0.1 into 100, we say total time I can assume here, which is can be neglected later. That means this is not giving absolute value in the rotations, but it is giving in that proportion. So this product is giving a value proportion to rotation. Multiply will be the T here, and this is 100 is 1, 400, 900 and 1600. We sum up and normalize it, what we can get a fraction. That fraction F1 for the first case is a 0.033, much lesser. That means this bearing is not operating at a much longer time for a much longer number of rotation of 4 kilonewton. That means happening only for the some time only. Maybe say some rotation, not sometimes some rotation. Coming to the second, the fraction is a 0.133 for 3 kilonewton. This fraction is a 0.3 on the higher side for the 2 kilonewton. A major chunk, a major number of rotations are happening at the 1 kilonewton. Now, if we use this relation in this equivalent load, what we get? P1 cube, that is a 4 kilonewton is there, is a heavy penalty on that, but this fraction is a lesser, so it's fine. The second thing is a 3 kilonewton over here. We need to substitute. P2 is equal to 3 kilonewton and F2 is equal to 0.133. For third case, what we are saying that this is a 2 kilonewton, P3 is equal to 2 kilonewton and F3 is equal to 0.3. Here in this case, a P4 is equal to 1 kilonewton, F4 is equal to 0.533. Naturally, we need to represent this kilonewton and newton. That means if we have to say P1 is a 4000, P2 is a 3000, P3 is a 2000, P4 is a 1000, and this fraction will be multiplied with that. When we take a cubic root of this, what we get, this equivalent load is a 2054 Newton, or this equivalent load is a roughly 2 kilonewton. And this can be shown out here. The major chunk of time is happening within the 1 and 2, and sometime it is a 3. So this is average is coming somewhere here. It's not in between. It's not a 2.5 because the fraction of the time which is spent on the 4 kilonewton and the 3 kilonewton is a much lesser than this fraction. So this is the equivalent load carrying capacity. We can utilize this to find out what will be the overall life of the bearing based on this. We will continue on the selection of the bearing in our next lecture. Thank you for your attention.